If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. So we discussed for real-world problem solving, it becomes imperative that we use a mix of models. And that's where we started talking about ensembling. So we've already talked about what are the broad categories within ensembling, and then we talked about bagging. Now we're going to discuss voting. How is it different from bagging, and what all does it offer? So first of all, as you can see, it's also a parallel ensembling technique, which means the various base models that you create here are all going to be independent of each other. Then what's different from bagging? First point, the base models are of different types. Then when it comes to data, each model is typically trained on the full training data, but predictions are combined through voting. So we are not doing any kind of bootstrapping, whether it be a row sampling or random subspacing or patching. We are not doing any of that here. So let's say our first model is a logistic regression model. Second model, which is another base model, could be a support vector machine. And the third base model could be, let's say, a decision tree. These are just examples. You could take any combinations of models. So that's clear. But there are two more factors that make voting really powerful. What are these? First is, we can assign weights to our base models. So maybe if you work in a particular sector or an industry, over a period of time, you build intuition that for this kind of data, these are the models that work the best. You can assign weights accordingly. Or you may realize that while looking at a performance factor, a particular model seems to be doing better compared to the other models, so you can accordingly give it a higher weight. That helps you improve the overall performance. So let's say if we know that logistic regression works very well for banking-related applications, and you have such data from BFSI domain, then you can say that logistic regression will be given a higher weightage compared to the support vector machines and decision trees. Likewise, if you have reasons to believe that support vector machines work better, you can accordingly adjust. And so is the case with decision tree. So if you have intuition or some sound understanding of the domain, which tells you that a particular type of model is supposed to do better compared to the other models, you can adjust the weights accordingly. And obviously, it's a strong player in the team. If you give it more responsibilities, highly likely that your overall results will be great. That's number one. The second aspect is hard voting versus soft voting. Let's look at these one by one. So hard voting is something that we understand through common sense. We have three models and each model predicts a class. So let's say the first model predicted a 1, second model predicted a 0, and the third model predicted a 1. Now, what is the majority voting? The majority voting said that for the given record, we should predict the class as 1. Why? Because 2 out of 3 models suggested that the class should be 1. This is simple majority voting, and this is called hard voting. If you look at the scikit-learn documentation for voting, you would see that the default there is hard voting. But there could be such models that predict the probabilities or likelihood. And there is more information hidden in the probabilities. So if you want to utilize that, you may want to go for soft voting. In soft voting, they look at the predicted probability. Let's say in our case, the logistic regression predicts the probability to be 0.6. Support vector machine says the probability is 0.05. And decision tree says the probability is 0.7. Please note these predicted probabilities are being referred to for the same observation or same record. And the models seem to vary. In this case, you can see that logistic regression and decision trees seem to be more in sync, whereas support vector machine seems to be totally different. Now, in case of soft voting, you don't really conclude it just like this. You also look at the predicted probabilities of the other class. So if it's a binary classification problem, then you can imagine it will be very simple to calculate the probabilities of the other class. It will be simply 1 minus the existing predicted probabilities. So 1 minus 0.6 becomes a 0.4, 1 minus 0.05 becomes a 0.95, 1 minus 0.7 becomes a 0.30. Now, which class we should predict finally? That's decided based on the argmax of the sum of predicted probabilities. So we have to first do a total of these predicted probabilities. Let's say for class 1, these are the predictions. Now, if you do a sum total, this comes out to 1.35. Whereas for class 0, these are the predictions. So if you sum up these, the value is 1.65. Primarily owing to a pretty high value here that we see. This is 1.65. So in this case, if you do an argmax, let's say this is for class 1 and this is for class 0, it'll say that class 0 attains a bigger value. And that's where your final prediction will be class 0 instead of class 1. It is said that soft voting is typically more meaningful when you're dealing with well-calibrated classifiers. So what is a well-calibrated classifier? Typically the kind of classifier that predict the likelihood. And the likelihood overall is more important for you compared to the individual class predictions. How do we deal with regression scenarios in case of voting? It's very simple. There is no hard or soft voting in case of regression. You simply average the values predicted. So that's the voting classifier for you. A lot of this will begin to make more sense when we do the hands-on exercise, as if not try to follow the differences between different kind of ensembling techniques. Please keep in mind, for all practical reasons, for real-world competitions and problem solving, ensembling is a preferred approach. And that's why we're exploring each and every section within ensembling to get further clarity.